Hi. Hi. My name is Adam Israelevitz, and with Patrick Lee, Jonathan, Krista, lots of other people, we've been working on a blank screen, Chisel. So as sort of the summary of Chisel 2.0 success is that we use it for all of our RISC-V generators. It's sort of been proven in our research that we've taped it out. Lots of interest from externally. And I think the best sort of way to describe it is Yunsep says, I love Chisel, and he's never going back to Verilog. And however, there have been some major problems with Chisel 2.0 because it was a research project. Most of these include it being monolithic, it's not systematically built, its IR semantics are not well defined. There's a blurry division between front end, back end, compiler passes. And because of that, you have poor error detection, incorrect input, what type of error message do you get? And finally, for our own research, we want to write these custom graph transformations, which I think we'll hopefully hear about. And it's difficult to write in the existing system. So we've decided to go ahead with a new plan, which we call Eden, which is basically an environment which all sort of target and can read and write Fertile, which is the new internal representation, a well-defined internal representation for the Chisel graph that gets constructed. So we reworked the compiler design to make these small modular transformations easy, to enable a variety of front ends, to enable a variety of back ends, and to enable custom transformations. So the idea is with a well-defined IR, sort of a lot of this research can take off. So it's divided into it's sort of one big IR, which we call the high-level Fertile, and that enables you to make a lightweight front end to generate these high-level constructs. And so you can make these lightweight front ends. And then there'll be some standard compiler passes which will translate these into simpler constructs within the same IR, and that can support lightweight backends. So you sort of have a funnel where you take in sort of more complex stuff and simplify it so that you have a lightweight backend. So with this, then we can do these custom transforms where you can insert stuff for debug, stuff for scan chains for detecting test coverage. These types of things you can make as an automatic transform to your Chisel graph of your circuit. So what's the status? We're really far right now. I just sent out the spec of the draft of the spec for internal review, and pretty soon we'll tech report it so that other people can write their own front ends and back ends. And right now it's just sort of taking on the process of porting to the new system, which we have strategy, and I'd love to talk to you about. So with that, if you have any questions, come to my poster.
Yeah, okay, so I'm Palmer, and I'm going to talk about Hurricane. So Hurricane is our new series of chips coming out of Berkeley, and the idea is that we're trying to go after kind of digital signal processing, right? So these are, kind of energy constrained. They have some real-time stuff going on, right? And they tend to have a lot of short integer computations, right? So usually you'd use sort of a, TI DSP sort of thing for this, right? And we've kind of thought about this a lot, and we went back and we looked at, this is kind of one of the, I guess, the original TI DSP, right? And it's not got a lot of stuff on there, and this kind of drove a lot of their design decisions, was fitting a 32-bit fuse multiply adder on a chip, right? And today things are a lot different. We have much bigger chips, and turns out that Huacha is a pretty efficient DSP engine, right? So we've demonstrated that with some of our previous research, and in the recent versions of Huacha, we've been adding short integer operations to it with all the mixed precision support, right? So the idea behind Hurricane is kind of, how do you make Huacha more efficient? You work on getting data into it, making it more decoupled, right? So we have a few features we're adding. So we have what are called virtual local store, which is a kind of better scratch pad in cache sort of deal. We have some per-core DMA engines, right, that allows us to get more decoupling, right? And we have this remote memory network, which allows us to scale the chip up over larger domains than you could efficiently do cache coherence, right? That's it. We're trying to get a tape out done, hopefully maybe middle of fall, end of fall sort of deal.
I'm Colin, and along with Albert and Yunsep, I've been working on Huacha, which is basically an elegant, performant, and efficient vector machine that we've done based on a lot of prior experience. So as you heard from Kirsta's talk, there's some problems with the current SIMD and SIMT models of execution, and so basically, we'll just summarize them. The vector length register helps a lot in terms of making your code easy to write and read. That also enables backward and forward compatibility, and along with this, we can use decoupling and prefetching to help hide the memory latency without needing all the threads or other things. We also have support for scalar values, much easier, and this allows us to avoid redundant computation and redundant storage in your register file. And all of this we can efficiently implement even on small problems. So what is Hwacha? Basically, it's a non-standard RISC-V extension that currently we've designed as a ROC extension, and so it hangs off of the Rocket core. And basically, the goal is to push an in-order vector design to its energy efficiency limit. So some quick features before I go into more detail. It sits in the same memory space as Rocket, so it's easy to move data to and from it, making it's coherent. It's also designed to work inside of an OS well, so you can context switch no problem. It's also a good compiler target, as in the same way that the vector extension that Cursor was talking about. So we plan on supporting both the SPIMD model and the auto vectorization support. Diving into a little more microarchitecture, there's a lot of extra features we have that we think make Hwacha more efficient than a simpler vector machine. So we have this scalar pipeline built in, which means you can do scalar computation and scalar vector computations all inside of the vector unit. Hwacha is designed as a very decoupled machine, so this helps us hide memory latency in multiple ways. In addition, we have the reconfigurable register file that we talked about before, so depending on the size of your machine and the size of your kernel, you get the best vector register you can, vector length you can. We also have mixed precision support, which ties into that so that you can operate on smaller data types and pack them more densely and operate on them as widening ops or in smaller registers. In addition, we have this concept temporary registers, which is kind of a new microarchitecture trick we have to better handle keeping this. It works well in scatter gather cases and things like that to basically set up temporary values that aren't live across your whole function or your whole vector set of instructions. But you can talk more about that at the poster. In addition, we've added predication, which Jensep has a paper on, and the OS support also spawned a paper from before. And come talk to me about all this at the poster.
Thank you. My name is Sam Falvo, and once again, I'm unaffiliated, but I do have a project. So my project is a home computer. It's a homebrew home computer, and historically it's always been built around CPUs of my own design, primarily because I want full control and the ability to fully document everything. And when RISC-V came to my attention, I realized that it met all of my goals, and I didn't have to do a whole lot of design work myself, so I kind of adopted it. Performance isn't going to be all that fantastic for first-generation hardware, about 6 MIPS or so why bother? And the reason is basically it boils down to the current state of PC industry. It's simply not hacker-friendly, and push comes to shove, everything's an appliance now. There are various reasons for this. I'm not saying that it's a bad trend, but I am saying that there is definitely a market for hacker-friendly computers, and I'm not currently seeing one that really meets my definition of a completely open, fully accessible computer. So the Kestrel platform is intended quite deliberately to rewind the clock and go back to an era when computers were simple enough that you can pick up one book from a bookstore about an inch thick and actually be able to program it at any abstraction level, whether it be from a high-level programming language all the way down to machine language, back in the days when they had timing diagrams for all the circuitry on board in one of the appendices of the book. So that's kind of the feeling and the user experience that I want people to have with the Kestrel computer. And if anybody wants to know anything more about that, especially more detail about my reasoning for kicking off the project or what I have in mind for future plans, I will be having a poster here, obviously, because I'm here now. And I look forward to speaking with people about that. Thank you.
Thanks. This should go on back. I'm Martin, and I have an update on the RISC-V Pokey Linux distribution. So RISC-V Pokey is our part of the Yocto project, which is a Linux distribution generator and a project within the Linux Foundation. And the reason we ported it was that traditionally bringing up software for RISC-V was kind of hard. You had to download the toolchain, compile it, download the kernel, compile that, find out all the dependencies, compile those manually until you finally got your software running and you could put it into your boot image. Now, Yocto does all that for you. It basically consists of a large number of what they call recipes, which know how to build different tools for different architectures. So what Pokey then does, it starts downloading all this software, applying patches, cross-compiles them for your architecture, verifies the output, generates Debian or RPM packages, and eventually creates an image for you. And we have used RISC-V Pokey to bring up quite a bit of software on RISC-V since the last workshop. Here I want to highlight one, which is our effort to bring up a JVM on RISC-V. So this is work that Michael Knischak, a student who's been working with us, has been doing for the last semester. Unfortunately can't be here today. But he brought up OpenJDK 7 on RISC-V using RISC-V Pokey. So this version is based on the 0 backend, which is interpreted, so it's quite low performance, but it's fully functional. And there was quite a few roadblocks along the way. One of them was, for example, you had to port the libffi library, which is responsible for foreign function calls between different language environments and actually requires quite a lot of low-level translating of code in RISC-V. However, with that and a couple of other patches, Java is actually running on RISC-V now and runs real applications, including real-world things like Zookeeper or the Scala stack or even Chisel. So that means we can now actually build a RISC-V core on a RISC-V core. So this is one of the Sodor cores compiling in a RISC-V QEMU in this case. Took half an hour, but it's a start. As I said, low performance. We are working on porting the JIT next. And it produces the C++ emulator in Chisel, and here's it running, actually passing all the RISC-V tests. So yeah, more on the poster.
Thank you. So what I'm here to show you is a vector engine that we've built specifically for FPGAs. And it's soft and scalable, so we can generate different size of vector engines with different number of lanes, and also with different amounts of internal state for compute. And this wasn't exactly meant for poster, but I'll quickly show you what it is. So it's built for FPGAs, as I said, and so for Xilinx it would be built on the AXI bus, and we can use a host processor of either the ARM core for Zinc series or a Microblaze. It's also fully compatible with Altera, Neos, and ARM. And what we want to do is make it compatible with RISC-V. So then with RISC-V, now we can have the same processor system running on Altera or Xilinx or Lattice or Microsemi or Acronix maybe. So we can have a common soft processor core across all the FPGA system. And we can also have vector acceleration through our engine. Our engine is two parts. We have the DMA engine and an internal scratch pad where the compute is going to compute from memory to memory on the scratch pad. The scratch pad is really like a RAID disk array. There's a lot of parallel block RAMs, and you're going to stripe your data across those parallel block RAMs and then read it out at high bandwidth, operate it on the parallel lanes, and write it back again. The DMA engine handles all the data transfer from the external DRAM into that scratch pad, and the DMA engine runs concurrently with the compute operations, so you can do full latency hiding by doing double buffering style prefetching. We have three different programming layers. One is a low-level C layer, which is like the instruction set. So there's an opcode like vector add, and what we operate on are pointers. So we give it pointers to the scratch pad, 2 source pointers and a destination pointer. There's an implicit vector length register, and that can be the entire length of the scratch pad. It can be 1 vector if you want it to be, or it can be 2 vectors. You could partition the scratch pad into as many vectors of any length that you want and mix them. It also supports mixed data types, 8 bits, 16 bits, 32 bits. The first parameter there, the VVW, is a type specifier. VV means vector to vector, so the 2 sources are both vectors. We can support a scalar to vector operation as well. And we have a special vector called an enumerated vector, which is the series 0, 1, 2, 3, 4 that we generate on the fly, so you don't have to store that. We also support different data types. So that W means word for 32-bit, and you can change that to B or H for byte or half word. And you could do data size conversion on the fly. You can operate on 2 half words and generate a word result. So you can use HW in that case. Slightly higher level C++ version where the type specifier is omitted and it's inferred from the vector operands and their data types. I should also add we have signed and unsigned and it's integer and fixed point, but no floating point natively yet. Thirdly, we have a high-level C++ object library, which simplifies things. Thank you.
Just get a little plug. Hey, I'm Austin Harris from Spark Lab at UT Austin. And my project is about adding counters to Rocket that directly measure contention. So side and covert channels rely on contention through microarchitecture resources to leak information. And so yeah, just come check out my poster, see what I added, and see how it can be used as a defense against these channels.
That was the end of the poster previews. Big hand for all the poster preview presenters.